Robot Talk is the podcast that sits down with roboticists from around the world and asks them the questions you always wanted answered. Like, can I feel what the robot feels? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week we're exploring how robot sensing, touch feedback, and novel, soft robotic designs can help humans and robots work together more seamlessly in scenarios ranging from surgery to search and rescue. But first, this is your regular reminder to subscribe to Robot Talk on your favourite podcast provider to make sure you're the first to hear the latest episodes. Another way to find out about new episodes is the email newsletter, which you can sign up to by going to robottalk.org. And if you sign up as a paid supporter on Patreon, you'll get early access to new episodes before they're released publicly. This episode is powered by the Advanced Research and Invention Agency's Robot Dexterity program, which aims to transform robotic capabilities and unlock a step change in human productivity. ARIA funds research that's right at the edge of what's currently possible across the full spectrum of science and technology. To explore the work they're currently funding, find out about new funding opportunities, and share feedback on their upcoming research programs, check out their website at aria.org.uk. So, without further ado, I'm excited to introduce this week's guest. I recently had a wonderful chat with Allison Okamura from Stanford University about developing advanced robotic systems for haptic interaction. This week, I'm speaking to Allison Okamura, a professor of engineering at Stanford University, working on haptics, teleoperation, and virtual reality for medical applications. Hi, Allison. Lovely to have you on the podcast.
Hello. Thanks for having me.
So you lead the Collaborative Haptics and Robotics in Medicine, or CHARM lab at Stanford. So to get us started, can you tell us a little bit about the research that's going on in your lab?
Yeah, the research in my lab is very human-centered. We're interested in robotics that help people across a wide variety of domains. Specifically in medicine, we're interested in surgery and rehabilitation. And then moving forward, a lot of our newer projects are related to assisting older adults, whether they're in the home or in a care facility. And the students in my lab come from a wide variety of backgrounds across engineering. And then we also collaborate with people in education, medicine, even folks who are working on oceans and sustainability.
Cool. Yeah, it's a really varied selection of work you're doing.
Yeah, so the research in my lab often involves humans in the loop. While I think autonomous robots are very interesting, I'm interested in robots that will either be driven by humans or directly interact with them. And so whether that's teleoperation or supervisory control or helping people interact with virtual environments and get more utility out of them, I just really love projects where there's a human involved.
Sure. Can you give maybe one or two examples of current projects you're working on?
I think one of the most exciting projects that we're doing right now is trying to rethink actually how people design robots. Historically, we have rigid robots with rigid links and joints that are in very specific places, but in both medicine as well as other human-robot interaction scenarios, having continuum robots, soft robots is really helpful. But it's actually very hard to design these robots. And with generative AI, I would love to find new ways of coming up with ideas for how to create new robots. What are the mechanisms? What are the materials we should use? But this process isn't going to be something like writing into ChatGPT, please design me a robot that does this. It should really be an interactive process with a human designer. And so one of our new projects is we jokingly call it the "Why didn't I think of that" project? Because we love it when we see someone come up with some very cool, interesting new robot design, and we'd love to accelerate that process. So this is sort of a meta level project in that we want to be able to have an AI design co-pilot that works with people and allows human designers to experience, interact with, and touch their robot designs in the process of being accelerated by everything that generative AI has to offer.
That's really cool. So earlier this season, I interviewed someone who's also looking at generative AI for robot design, for robot grippers, which is very cool. And yeah, previously I've interviewed some people who do like robot evolution, which again, it's really interesting to see when there's a different designer in charge, what ideas they come up with that you would never have thought of.
Yeah, I think one of the most interesting things to see is what will happen in terms of generative design being used for truly new mechanisms. I think in the past, people have used it either to do kind of optimization of an existing design, which is also really helpful, but not maybe quite as sort of creative and revolutionary as we'd like to be. Kind of want to do the Fosbury flop of robots, like a totally different way of thinking about how to use a robot to solve a problem. But the problem in the past, I feel like with many of the robot designs that have been used creating evolutionary algorithms and such, they're very cool and compelling, but somehow they're not very practical. Like they're not the things that someone wants to make into a product. No one seems to want to buy those robots. And so what I'm hoping is by finding ways to keep the human more directly in the loop, that we can come up with really new robot designs and mechanism designs that are things that people want to use. And an example of that could be, for many years, my lab and many other labs have tried to design really tiny snake-like surgical robots, little instruments that can go into the body, into the vasculature. And it's very difficult to come up with mechanisms that can operate at that scale, but still have some dexterity. And every, I would say, 5 to 7 years, someone comes up with a new mechanism that I think is really cool. But if you think about it, 5 to 7 years is kind of the generation of a PhD student. Yeah. And it would be really great if we could accelerate that design process and come up with these devices that could really be important for applications like surgery.
Yeah. You sort of mentioned the fact that, generative processes kind of, the outputs are maybe missing something that's kind of hard to put your finger on. It would be really interesting to see if with this feedback loop between AI and a human, you can kind of eventually train in those things that maybe we can't put into words why the human designed robot is better, but we can create it in AI with enough training and enough practice.
Exactly. And I think it's really important to understand people in this process. So we don't just collaborate with engineers and clinicians on this, but also we have an amazing psychology collaborator, Judy Fan, here at Stanford. And she's really giving us a great perspective into the human design process and how we use visual and spatial information in order to come up with better designs.
Yeah. And you mentioned soft robotics as being, something that you're working on now. I think it's interesting. I've been doing this podcast for 6 years now. And when I started, it was very much like you had soft roboticists and then you had quote unquote normal roboticists. And now I'm finding so many more people. It's just soft robotics is becoming part of the toolkit rather than like its own separate discipline. I think that's quite an interesting evolution of things.
Yeah, absolutely. I think with soft robotics, what people are realizing more and more is that in any robot, you have parts that you want to be soft and parts that you need to be rigid.
Hmm.
I think an interesting direction for the field of robotics, especially right now, as there's so much more investment happening, is to understand where we want general purpose robots. Like a lot of people talk about it, a humanoid as a general purpose robot. Versus a robot that's very specific for one purpose. And as another example of things that we're doing, I'll give an example of a very specific purpose robotic system. We have a project sponsored by ARPA-H, which is the Advanced Research Projects Agency for Health in the United States. And the goal of this project is to 3D print a biological heart. And the idea there is the 3D printer is a little bit like a classical extrusion-based 3D printer where you feed material through thin tubes and you lay them down in patterns. But now that material is going to be a biological set of biological cells.
Wow.
The interesting thing with why is a 3D printer a robot? The idea is that in order to do this very quickly, we need to have lots of little tentacle-like print heads where the material is fed through all of these print heads at once. And they have to be able to not run into each other. They have to be able to respond to deflections and non-idealities in their performance. And this is a really exciting project because the idea is we can build a 3D printed heart in less than an hour, which is required. You have to do it really fast before the cells die.
Right.
And so it's a very different type of challenge for 3D printing, and it requires a bunch of techniques, control, planning, et cetera, that come from the robotics field. But that is a super specific purpose robot. It's a robot that can 3D print these special materials, and it's totally different from a humanoid, and yet it's extremely useful. So this kind of robot that I'm describing, it's a combination of rigid and flexible parts, and you just kind of build the robot that needs to be built in order to do a particular task. And there's this whole spectrum of robot designs. And I think more and more folks are starting to say, okay, let's not just take an existing robot design and try to use control and intelligence to make it do other things, but let's have this sort of mind-body connection to have just the right robot and just the right intelligence for a task that can do something really, really well. I'd rather have a robot that is kind of the master of one trade rather than the jack of all trades. And especially in medical applications where accuracy and safety is so important, I'm willing to give up that maybe flexibility of a general purpose robot and think about the spectrum of different mechanical properties of a robot and tune them just right to make sure you can do a procedure like 3D printing a heart or like surgery.
Yeah, I love that example. That's so sci-fi, but so impactful if it can work.
Yeah, the goal is in another year and a half, we'll actually be able to 3D print the heart with biological tissues.
Wow.
So you can come back to me in a year and a half and we'll see where it is.
Amazing. I will do. So, haptics has been a big part of your research, and the sense of touch is such a crucial part of how we as humans perceive and interact with our world. It's one of those things that I think we take for granted. We don't really think about it, but it's just there, and it's hugely important. Can you talk a bit about the challenges of making robotic devices that can sense touch, and also, as you mentioned, all the kind of importance of humans in the loop? Kind of how do they then relay that information to a human operator?
Yeah, absolutely. So the sense of touch, you're totally right. It's kind of underappreciated. We find it difficult to imagine what life would be like without touch, right? You close your eyes and maybe you can imagine what it would be like without vision. And you can plug in your noise canceling headphones and play white noise, and you can imagine what it feels like not to hear. But touch is a bit difficult to imagine. But one of the examples I often use for humans is that if you are trying to button up your jacket in the cold, you often are very fumbling. It's very difficult to do that task. And a lot of people think, oh, it's cold and it's because my muscles have gotten cold and my muscles aren't working right. But actually, the problem is that at relatively reasonable temperatures, not ones that would damage the skin, but the kind you might encounter if you just go outside on a cold day, it's cold enough to knock out some of the mechanoreceptors embedded in your skin. And what you lose is knowledge of the contact condition between your fingers and the objects you're manipulating. So if you're trying to button your coat or zip up your jacket, you fumble. And so one of the things I use as an example for people who are thinking about, why can't robots do some of these dexterous manipulation tasks? It's like, well, imagine if you didn't have really good tactile sensors all over your skin. And of course, folks are pushing more towards tactile sensing on robots, but most robot hands, and especially humanoids, don't have that kind of sensing integrated yet. And one of the challenges, I would say, in doing that for robots is just that the kind of tactile sensing humans have is so multifaceted. We have a bunch of different types of these mechanoreceptors. They respond to different stimuli. They respond to different frequencies. And we just haven't been able to come close to recreating that in an artificial tactile sensor that you would put on a robot. We have some parts of it. And even those parts tend to be a little bit clunky, but there's a lot of really great ongoing research and even startup companies that are starting to get there to have an array of tactile sensing data that might actually be in a form factor and be low power enough that can go on some reasonably sized robot hands. But I'll say all of that is more about touch sensing for robots. The challenges for giving touch feedback to humans is a different thing, and maybe I can talk about that a bit.
Yeah.
So with touch feedback to people, it might help to talk a little bit about the history, which is back 30, almost 40 years ago now, people were designing what are known as kinesthetic or force feedback desktop devices, which basically look like small desktop robots. But instead of moving around autonomously, the idea is it's like a manipulandum. You grab onto the end effector as a human and you move it around, you back drive it. And then the motors would generate forces to create sensations like, oh, you're touching a virtual object.
Okay.
So the challenge with these types of haptic devices is that you have to let the human do what they want. The human has to move around and explore that virtual environment or teleoperate a remote robot. And you want to let that human do what they want to do and then provide them the force feedback through the motors of the haptic device that is correct for whatever action they're doing. But the human can do, it's exactly that problem. The human can do whatever they want. They're kind of unpredictable. They might move fast. They might move slow. They might want to, touch gently onto this virtual environment, or they might want to hit it really hard. And it's difficult to have devices that really have these two almost conflicting properties. One is stability. You want to make sure that the device that's generating forces doesn't start vibrating uncontrollably or create forces that are unrealistic. So you need this stability, but you also want to have what we call transparency. So you want the things that the human feels to feel exactly like what you wanted that virtual environment or remote teleoperated environment to feel like, so that it's reflected exactly in terms of the human's perception of it. And in order to have that kind of perfect transparency on a controller, it's like turning up the gains to an infinite level. Even something like the desk in front of me, if I tap on it, you hear a noise in part because of the pressure waves that are coming off of the surface. And that is, in a haptic sense, a really hard task to create that kind of really stiff surface that generates vibrations, but yet is very stable and reliable and repeatable. So this transparency versus stability trade-off has always been a challenge for haptics, and it's really just a fundamental sort of controls limitation. But I think the interesting thing that's happened to haptics over the years is we've moved away from these traditional desktop devices that are like traditional robots, and now moving on to wearable devices.
Okay.
And those are a little bit easier to keep stable because they're not sort of pushing back on the human body in a wholesale way. They stimulate the skin, but that doesn't necessarily cause the human body to move and close a control loop that sometimes causes instability. So these wearable haptic devices, we have more kind of skin real estate to use. We can use parts of the body like the forearm or even where we put our watch that maybe aren't normally used. We can spread that information out into different locations. And they're more about transferring information to the human rather than pushing the human around. And that's creating really great opportunities for new types of haptic sensations that maybe are a little bit safer, or we can push the stimulus to be more compelling because we don't have the same stability problems as we do with traditional haptics.
Okay. Yeah, that's really interesting. Thank you for the kind of history of the field there. I was just thinking, like, how essential is perfect transparency of the signal? Because, you know, my phone vibrates and it kind of simulates a feeling of pressing a button, even though I haven't pressed a button. And I've kind of, my brain has learned that that's what that means. But then I can see if you're talking about like surgery, it's much, much more important that you really feel an accurate representation of the tactile sensations.
Exactly. I think it totally depends on the task. If you're doing surgery, you probably want to know exactly the forces you're applying to the patient. But it's really only quite recently that widespread commercial surgical robotics have had really good haptic feedback within them. And even then, the gains are turned down a bit to really ensure that safety and stability, because we still have that contrast in the way that surgical robots are designed. However, there is this information transfer idea, right? That my watch and my phone vibrates. It gives me a cue. Maybe it tells me which direction to turn. Maybe it tells me someone is calling. And it's a very different purpose for haptics. Often that can be more event-based, like it's just trying to get your attention as an alert. And I think a challenge for the haptics field is moving that type of informational display away from just an alert, which is usually there to ask you to then look at it and use another sense like vision, or maybe answer the phone and then use sound. But rather, how much information throughput can you provide through haptics? And vibration is a great example because vibration actuators are so ubiquitous now and cheap. And we have mechanoreceptors embedded in our skin that are super tuned to notice vibrations. And so you kind of get a lot of bang for your buck out of vibrations. But those vibrations in many real world tasks is not really what you want. It's not realistic. People also kind of adapt to vibrations and don't notice them after a while. Or on the other hand, they get really annoying. So one of the things that we've really been pushing over the last decade or so has been skin deformation haptics. So for example, if I pick up my phone and I squeeze it, I don't only feel normal pressure between my fingers, but I also feel the stretch of my skin due to the weight of the phone. And it's that sort of vertical stretch that I feel against gravity that tells me a lot of information about the weight of the phone. It's the stretch in the skin, not necessarily so much the muscles and the joints further down on my arm. And so it turns out you can do this skin deformation stimulation locally, not just on the fingers, but on other parts of the body that give humans a lot of very realistic cues, even without having these desktop kinesthetic devices. If all you need to do is deform the skin, then that can actually become a wearable device. And it is challenging to make these devices, but that's where the connections to soft robotics is actually coming in.
Yeah, I mean, I guess, you know, coming back to what we were saying before about how complex the human sense of touch is, that gives you a lot of opportunities for different ways that you can stimulate it with haptics.
Yeah, that's right. Because human mechanoreceptors have all of these different properties.
Yeah, exactly.
You can deform the skin, you can vibrate it, you can apply larger forces over joints, whether it's from a desktop device or even an exoskeleton. You have all of this skin real estate all over the body, much of which is unused. Of course, there are these dreams, and even some companies are developing full-on haptic suits. But the big challenge there is going to be, how do you make those things comfortable? You don't want to sit there sweating in it. So another one of our projects that we've been working on over the past few years have been knitted-based wearable haptic devices. So collaborating with an amazing group at MIT that is an architecture, and they really think about unique knitted architectures. And so we've been embedding pneumatic air-based haptic stimulators into novel knitted fabrics that are much more comfortable to wear. They're breathable. They better adapt to humans of different sizes. So you don't want to feel like you have to put on a neoprene suit or even a rigid exoskeleton every time you want to don a wearable haptic device. And so going back to even traditional methods with textiles like knitting has been a really unique but successful way of making these devices more wearable.
Yeah, that's really cool.
I'll mention one other topic that I've been super excited about. It really got started initially because of my interest in rehabilitation and haptics, and it is, how do you put these devices on the body, especially for people who want to use a device for rehabilitation? They may not have the motor skills to actually put a rehabilitative device onto their body.
Yeah.
So we've been making these self-wearing garments or self-wearing clothes, which are fabrics that get onto the body in various ways. One way, imagine you pull off your sock. When you pull off your sock, it turns inside out, right? So we have a way of essentially reversing that process where things like socks and pants and jackets unfurl onto the body using air pressure. And that is a really fun project. We have not yet achieved our dream of making rehab devices or wearable haptic devices go on the body that way, but we can make specialized clothing automatically don onto the body. And our next phase of this is to make self-donning clothing that use zippers in really unconventional ways. So imagine a zipper not just to close the front of your jacket, but one that zips together multiple panels of clothing so that if you have arthritis and you can't put your arm over your head, you could just hold your arm a little bit and the clothes would sort of zip together and self-assemble onto the body. So we have these dreams for, eventually self-wearing devices that are robotic, assistive, or haptic devices. But even just making self-wearing clothing where the clothing itself kind of is a robot is another way to help people with limited dexterity or mobility.
That's so interesting. It must be quite a strange experience to have a piece of clothing put itself on you.
Yeah, it's pretty fun. Some of my students, I have one student in particular who loves cosplay and is a costume designer and knows how to sew and is also interested in using these techniques to make self-donning clothing for robots as well. People like to put humanoids in clothes sometimes, but it takes a human to put those on.
Yeah.
And so the self-donning clothing for robots will also be quite interesting. But I was going to say that, some of my other students have never touched a sewing machine before. And so we have some pretty awful looking pants that don't fit very well as our first try. But as we're getting more and more into these self-wearing garments, we're definitely learning more about textiles and how to sew and pattern and be able to create robotic clothing for both humans and eventually robots.
Yeah, I mean, it just goes to show how multidisciplinary robotics really is.
It is. And that's one of the things I just really love about this field. It's one that takes all comers. You can be an engineer, you can be a fashion designer, you can be in education or medicine. It's just a field that needs people from all backgrounds to give input. Really, anyone who has any kind of expertise in any domain, I think, can really inform what robots can and should do.
Absolutely. So as well as applying your work on haptics to medicine and rehabilitation, you're also working on applications in remote and hazardous environments. So can you tell us a little bit about this aspect of your work?
Yeah, there's a couple of projects we have putting robots in remote and hazardous environments. Probably the most well-known one is this device we call a vine robot. It's
Okay.
basically a tube of soft material. Imagine something the consistency of a Ziploc bag. And if you put it in a tube form and you kind of stuff that tube into itself and then you pressurize it, the material wants to flip back out. So it everts, which is the opposite of inverting. It flips inside out and effectively grows. So we call these soft growing robots. And we originally developed these for a totally different purpose to try to make some simulated organs that change their length. But it turns out that this is a really good technology for doing things like exploring pipes or going into rubble for search and rescue. So I have some students who have a startup company actually using these robots to go many meters, someday even hopefully hundreds of meters, into pipes to do inspection in locations that you just couldn't do any other way, non-destructively. Especially pipes that are small and are tortuous, that have curves. These are just places where people can't go. And these vine robots, they can go against gravity, they can steer when they encounter junctions, and they can basically get to places that no other robot or human can go. So we're very excited to see this applied to, for sustainability purposes, to make sure our water infrastructure remains sound. Also in other scenarios where you want to inspect pipes and make sure there won't be a leak, we want to be able to get places to make sure that pipes are more sustainable and the infrastructure can last longer before it has to be destroyed and rebuilt. So that's one area, is this kind of inspection task. The more challenging thing is to go outside of pipes and inspect in free space, whether it's rubble or the robot has to kind of support itself against gravity. And that's something we're still working on, but we have now ways of actuating vine robots. And I say we, not just myself, but many of my former PhD students that have their own labs have invented a wide number of ways to be able to steer these robots in free space. And it's just a little bit challenging because you have this robot that you want to be able to be soft enough to evert and kind of flexible enough to turn inside out and have this growth property, such that you get propulsion at the tip, but it still needs to have some kind of actuation that helps it to steer, especially at long distances, and has to be powerful to lift against gravity. And I think as many of the folks in the field are working on this, my hope is that pretty soon we'll have some really unique new search and rescue robots that will be able to reach and help people in terrible disaster scenarios.
I mean, my first concern with a kind of inflatable robot in a rubble or that kind of environment is punctures.
Yeah. So an interesting thing about this vine robot technique is because it unfurls from the tip, it doesn't have any sliding with respect to the environment. So it's not like a classical snake robot that has to use contact with the environment and it slides with respect to things. So we've done things like grow the vine robot basically through a bed of nails, I guess a bed and a ceiling of nails, where the nails actually puncture the vine robot. But what happens is that because the robot is not sliding with respect to those nails, the nails actually kind of fill the hole that they puncture into it. And there's a little bit of air leakage, but you increase the flow rate a little bit, and then the robot can actually keep growing as long as there's not really, really huge holes torn open. But the holes don't want to tear themselves open further. So this particular design just has this unique property in that it's a little bit robust to this.
Yeah. So you're also interested in applying haptics in educational settings to teach students about subjects like maths or physics in a more intuitive way. So what would haptic learning look like in practice, or feel like in practice, I suppose?
Yeah. So Learning, I feel like, is a really multimodal experience, right? You listen, you see. They always say that, what you speak, you learn more. And I feel like part of the reason I became a mechanical engineer is because feeling things with my hands was always an intuitive way of learning. And so we've developed haptic devices for grade levels, ranging from elementary school all the way to professionals, to help them use the sense of touch to learn about things. And sometimes it's very literal. For example, if you want to teach a student in, say, mechanical engineering about springs and dampers, you can create a virtual environment where you can feel a spring and you can change the stiffness, and then you will feel something different. And then you can combine the spring with a damper and understand viscoelastic behavior. So you can create these virtual environments where people can kind of, play God with mechanical properties. You could even ask something like, well, what would something feel like in terms of its weight if I was on a different planet? And how is that weight different because the gravity is different, but yet the inertia as I move it around and accelerate it with my own hand, how does that remain the same? And so I think you can create these experiences in virtual environments that are very difficult for us to experience in real life that provide this intuition about physics that you might not get in another way. So that's a very literal way of using haptics to give educational experiences. There are other ways where you can kind of do training or matching. I had a former postdoc that used vibration feedback to help people understand the patterns they would need for piano playing.
Okay.
And so even novice piano players could learn patterns through this passive haptic stimulation. And that's also a technique that we've been applying to helping students, really young students in elementary school, learn to count and add in group numbers. So kind of connecting the 10 fingers with vibration actuators, which would help them understand better how they are counting and learning numeracy concepts with their fingertips. And of course, this is not something, my lab can do alone. We have to work with experts, whether they're in education or educators themselves, education researchers, as well as educators.
Yeah, it's a really cool idea that I would never have thought of, but I love it. And I definitely want to try it out sometime.
Absolutely. That's one drawback of a podcast is you can't feel the devices.
Yeah.
But yeah, I'm hoping all your listeners get the chance to maybe go to a robotics conference or even better, a haptics conference, because at haptics conferences, demonstrations are super important. So every haptics conference will have a big demonstration session, and that's really the heart of the conference. Because unlike, say, a graphics or vision conference where you can show everyone images or videos of what you've done, we really want people to feel and interact with our devices to understand how they perform.
Yeah, absolutely. Allison, it's been great chatting to you today. I've been talking to Allison Okamura from Stanford University. Thank you.
Thank you for having me.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. And check out @Robot Talk Pod on social media to see a photo of Haptiknit, a wearable, soft, knitted haptic device that Allison's been working on. Make sure you tune in next week to hear the recording of my panel discussion on robotics and AI in medicine and healthcare. Recorded live at the Great Exhibition Road Festival in London earlier this month. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk Season 6 is sponsored by the Hamlin Centre, Imperial College London.